Hello and welcome to this talk. In this talk, we'll explore what might lie beyond convolutional networks in the history of computer vision. So here is a canonical structure of a convolutional network. This is the VGG network, and you see the familiar elements here. The workhorse of the model is the convolution and the convolutional layer. Here the blue layers are convolutional layers, and they perform the bulk of the processing. It is not called convolutional network for nothing. The convolution really does the bulk of the work. You also see another characteristic element of the model, which is the concept of layer itself. The model is built out of layers. One layer follows another. It has a kind of wedding cake structure because the resolution is decreased in later layers, although the wedding cake structure itself is perhaps less essential. There are architectures that don't have this wedding cake structure. They might have an hourglass structure or another overall macroscopic shape, but the concept of layer is really foundational. Convolutional networks are built out of layers, and in our conception of these models, each layer produces a feature representation that is then passed to the next layer, that in turn processes it, produces the next feature representation, passes it to the next layer, and so forth. We are going to question these assumptions in this talk. Before I do that, let me clarify that I love convolutional networks. The work that you will see presented today is not driven by some kind of vendetta against convolutional networks. I'm a big fan of convolutional networks. I have worked on convolutional networks and have applied convolutional networks in many projects, and I really am a big fan. The work that you are going to see today is really motivated by basic curiosity. Convolutional networks have been so successful that we can wonder, is this it? Is this the end of history for computer vision? Is the rest of computer vision just going to be applications of convolutional networks, perhaps with minor variations on the theme? And what is the theme? Well, there are two ingredients that we are going to focus on today. The first is the convolution operator itself. The convolution operator is shown on the left. It is the very basic operator in convolutional networks. And in the first work we're going to see today, we're going to question whether we need the convolution. In the second work, we're going to look at the very concept of layer. We are going to question whether we actually need this layer-wise architecture that many of us take for granted and in fact associate with the concept of deep learning itself. Why is it deep? Because we have many layers. So let's proceed to the first work. The first work is presented this week at CVPR 2020, and in this work we look at the convolution. Now, the convolution, although it is wonderful and elegant, and I personally love it, is not without its drawbacks. For example, the number of parameters in the convolution operator grows with the footprint of the kernel, with the receptive field of the operator. So for a 3x3 convolution, we have a certain set of parameters, but if we want to do a 7x7 convolution, we now have a very different set of parameters, a much larger set of parameters, and this is something that we actually need to determine at training time, the time that we're designing the architecture. The processing of information from the image, the aggregation of content from the image is essentially blind at test time. It does not adapt to the image content. When you take a convolution, a trained convolution, as in a convolutional network, and you apply it to two different images, the information is aggregated in exactly the same way. Exactly the same weights are applied regardless of the content of the images. No matter what the image contains, the convolution will do exactly the same thing. It will take weights, it will take information from neighboring pixels in exactly the same way. Now, our inspiration for reconsidering the role of convolution in computer vision and state-of-the-art computer vision models comes from natural language processing, which has seen a revolution in the last few years. And this revolution was wrought by transformers. Transformers are one of the most interesting stories in deep learning. They have revolutionized natural language processing. These are a genuinely new class of models, a genuinely new architecture that has displaced other architectures for natural language processing. They were only introduced 3 years ago, but in this time they have gone from the design table to production and are now used at scale and have essentially cast aside other approaches to natural language processing. At the core of transformers is the self-attention operator. And for the purpose of our presentation today, I really would like to try to zero in on the essence of the self-attention operator. So I'm going to set aside many details and possible variants and really look at the essence of what the self-attention operator does. And in essence, the following type of information aggregation happens in a self-attention layer. We have a data point X. The data point is localized at a certain point in feature space. There is a metric space in which the data points live. In this metric space, the data point X looks around at its local neighborhood and sees other data points at various distances from itself. It computes the distance from itself to other data points, and that distance is used to determine the weight with which information is going to be aggregated from those other neighboring data points. So the point X looks around and sees there is a point Y3 that is pretty close. It's going to compute the distance between X and Y3. That is going to determine the weight at which the point X takes the feature from Y3 and aggregates it. So the weight with which the feature from Y3 is taken by X is determined by the distance between X and Y3. Likewise, for Y2, the feature at Y2 is going to be taken by X with a weight that is determined by the distance between X and Y2, and so forth. So X will get a weighted combination of features from other points, where the weight for each point is going to be determined by distance in feature space. Note that there are two kinds of features here. One is the metric space in which the data points live and at which the distances are evaluated. That is one kind of feature space. Another feature space is the features that each data point carries, the features that are actually aggregated. Those don't have to be the same. Think of each data point as carrying a payload. So a data point lives in a certain location in feature space, but it also carries a payload, which is a different feature vector. And that payload is going to be aggregated with weights that depend on distances in the first feature space, not the space of payloads, but the space of locations. Now, let's look at some properties of this self-attention operation. First of all, let's realize that the self-attention operation is fundamentally a set operator. It proceeds based on distances in feature space, and it basically disregards which location in the original image or in the original sequence or in the original data set each data point came from. So in the context of image processing, you can take a patch centered around a pixel and look at all data points in that patch and process them with self-attention layers, and you are not indexing specific data points based on location. This is very different from the convolution that really does things like take the pixel that is to my left, attach a weight to it, a weight of, let's say, 0.3, and take the feature from this location, from this image location, with this predetermined weight 0.3. Well, the self-attention operator does not do that. It does not index data points by image location. It also doesn't attach specific weights. The weights are determined at test time depending on the content of each data point, depending on where it ends up being placed in feature space by preceding layers. So this is very different again from the convolution. The convolution really learns specific weights per image location, and these are the weights with which information from that location is going to be aggregated no matter what. The self-attention is different. It adapts the weights to the content of the image and the content of each data point. As a set operator, the self-attention is invariant to permutation and cardinality. Note that the number of data points that end up in the neighborhood of X here is not predetermined. You could have maybe 3 data points, you could have maybe 10 data points. And in fact, that receptive field can be changed at test time, potentially with no retraining. Since we're not indexing into specific image locations, and since we're not learning dedicated weights for specific image locations, we can adaptively change the receptive field of our information aggregation without potentially even having to retrain the network. The core idea in our self-attention networks is that the convolutional layer in convolutional networks really bundles 2 functions. We refer to them as feature aggregation and feature transformation. The convolution operator itself performs feature aggregation, and this is an operation that has to have spatial extent. This is the operation that intermixes information from multiple locations in the image. The second type of processing that the convolutional layer performs is feature transformation, which introduces nonlinear decision boundaries into the decision space, into the feature space. Usually in convolutional networks, these are bundled together. So we have a convolution operator followed by nonlinearity. This bundle of processing performs both feature aggregation and feature transformation. In our self-attention networks, these two functions are decoupled. The feature aggregation is performed by self-attention, by the self-attention operator. The feature transformation is actually easy. It can be performed pointwise. It doesn't need to have a receptive field. It can simply be performed on each data point by perceptrons, by sequences of perceptrons which introduce nonlinear decision boundaries that shatter the feature space and allow very complex decision landscapes to form. We have a number of technical contributions in this work, which include introducing a more powerful family of self-attention operators. The key idea is that self-attention operators that are commonly used in natural language processing, in transformers and the like, compute a scalar weight for each data point. Remember those data points y from which x took information? Well, that information was weighted, and it was weighted by one weight that was applied to the whole payload carried by y. We introduce computationally efficient self-attention operators that in fact compute different weight for each channel in the payload, in the feature vector. We call this vector attention, and it is much more expressive than the scalar attention used in prior work. Furthermore, we show that we can combine aspects of convolution and properties of self-attention into a new family of operators that we call patchwise self-attention, which are a strict generalization of convolution. So they are no longer set operators. They do index specific image locations just like convolution, but they are also adaptive to the image content like self-attention. And this patchwise family of operators is much more powerful than either convolution or self-attention alone. Let's look at some results. Here we're going to compare our self-attention networks to ResNet baselines on ImageNet classification. And the way the self-attention networks are constructed are by just taking standard ResNets like ResNet 26, ResNet 38, ResNet 50, and basically replacing convolutional blocks in ResNet by our self-attention blocks that use the self-attention operators instead of convolutions. So all convolutions are basically replaced by this self-attention aggregation that operates in feature space, that adapts to image content by computing weights based on distances in feature space rather than based on indexing into specific image locations. Let's focus on this middle block, where a ResNet 38 baseline is compared with a corresponding self-attention network that was constructed by essentially taking ResNet 38 and replacing convolutional layers with self-attention layers. The ResNet baseline gets 76% top 1 accuracy on image classification. The pairwise self-attention network, meaning the self-attention network that uses the set form of self-attention, it does use our more powerful vector attention operator, but it is fundamentally a set operation. We do not give up on the permutation invariance and cardinality invariance here. In this middle row, we use this pairwise form of self-attention that's basically a set operator. That's in the middle row. And look at this. The self-attention network outperforms the ResNet baseline. It's actually much lighter and has a much lower number of parameters. It has a comparable number of flops, but it reaches and in fact somewhat surpasses the accuracy of ResNet 38. This is remarkable because this model does not use the convolution at all. There is no convolution. And in fact, the basic operator is structurally dramatically different from the convolution because it doesn't refer to image locations at all. It does not index data points by their location. It never says, oh, dear pixel, look at the pixel to your left and take information from it with a certain weight. None of that is done. There is no concept of to your left or to your right or above you as with the convolution. Now let's briefly also look at the bottom row where we see even stronger results. This is the patchwise model. It's just like the pairwise self-attention, but it now uses our patchwise self-attention operators that are a strict generalization of the convolution that also adapt to the content of the image. So they incorporate ideas from both convolution and the self-attention operators. This now is no longer a set operator, so it does inherit some of the limitations of convolution in that it has to operate on grid structured data. It does index data points by location. But look at the accuracy gain. We're now 2 percentage points ahead of the ResNet baseline, which is a remarkably successful convolutional network. Let's look at another experiment. Here we applied an adversarial attack to already trained models. And these are the same models that you saw in the previous slide. We have the ResNets, the pairwise self-attention networks, the patchwise self-attention networks. They were not trained for robustness. They were just trained for image classification on ImageNet. That is it. So now we apply an adversarial attack at test time to see how easily an adversarial attack can destroy these pre-trained models. We apply the adversarial attacks by Alexander Madry and collaborators. Let's now look at the central row, the central block here, which are again the same kinds of models that we saw that we examined in the last slide, the ResNet 38 with corresponding self-attention networks. And And let's look at the strongest attack among the ones we tried, which takes 4 attack steps. So the starting accuracies with no attack before any attack are shown here on the left, and the resulting accuracies after the adversarial attack are shown on the right. And you can see something amazing. The ResNet baseline is essentially destroyed by the adversarial attack. The accuracy after 4 attack steps collapses from 76% to 4%. On the other hand, with no special training for robustness, the self-attention networks actually retain non-trivial levels of accuracy, highly non-trivial in comparison with the convolutional network. They stay around 20% top 1 accuracy even after the attack. So there is something structurally different that protects these networks. What is it? We think that it is the adaptation, the adaptivity to image content at test time. The ResNet functions essentially like an open loop controller. After training, it's just flying blind. After a ResNet is trained, it is going to apply exactly the same pre-trained weights to any image it gets. This is like open loop control that does not incorporate information from the signal at test time. And as we know from control theory, open loop controllers are essentially brittle. They are intrinsically brittle and very easy to cripple. On the other hand, the self-attention networks, due to the properties of the self-attention operator, are more like closed-loop controllers. They actually do look at the signal that they are processing and adapt their weights at test time to the signal. We believe that that is what allows them to retain non-trivial levels of performance despite a dedicated adversarial attack. So the takeaway so far from this first part of the talk is that we can match the accuracy of convolutional networks, strong convolutional networks on image recognition, without using convolutions, and in fact with a set operator, which is structurally very different from the convolution. This is remarkable because this suggests that an alternative history could have unfolded in which the deep learning revolution occurs even without convolutional networks. This suggests that there is basically a scenario in which convolutional networks perhaps were not invented, would not have been invented, but the deep learning revolution proceeds nonetheless. And we reach the levels of performance that we are observing in computer vision today, even without convolutional networks and without convolution. Now, this is not the world we live in, and this is not the history that occurred. And I love the history that did occur. I'm a big fan of convolutional networks. But I also find it remarkable that there appears to be a very different, almost independent path to the levels of accuracy that we are observing in computer vision today that does not depend on the convolution at all. There is a hopeful message here for applications of deep learning on unstructured data or data with a very, very different less regular structure, such as graphs, sets, and point sets, as in 3D deep learning, for example. Now, deep learning has been making substantial advances in our ability to analyze and synthesize graphs, sets, and point sets. But the work in these areas has been accompanied by a sense that we are perhaps in an uphill battle, that we are at a kind of disadvantage when it comes to applications of deep learning to graphs, sets, and point sets, because the data does not lie on a grid, because we cannot index into data points by location. There's been a sense that we are at a kind of disadvantage compared to image analysis or sequence analysis, where the data is arranged so nicely on a grid of some dimensionality. Well, our results suggest that maybe these areas where deep networks are developed for graphs, sets, point sets, and other irregular structures are actually not at a disadvantage, because this indexing into grid locations is actually not essential to the success of deep learning, even on images. Finally, I will mention again the technical points that we developed in this work that are quite interesting, and I will refer you to the paper for the details, which are the vector attention operators, a genuinely new, powerful family of self-attention operators that adapt to different channels in the feature vectors that are being aggregated, and the patchwise operators that strictly generalize the convolution by bringing in adaptivity to the content of the signal that characterizes self-attention operators, and essentially marry some of the strengths of the convolution and of self-attention. That concludes the first part of my talk, and I will now proceed to the second part, in which we will look at the recent work with Xiaoji Bai and Zico Koltun on multi-scale deep equilibrium models. And in this work, we are going to question the other underlying assumption of convolutional networks, which is that deep networks are composed out of layers. This seems almost too obvious to state. Of course, deep networks are composed out of layers. That is why they're deep. Well, we're going to take a second look at this. In general, layers really seem absolutely central to the agenda of deep learning. The story we all tell is that a deep network is composed out of layers. Each layer takes features from the previous one, processes them, computes features that are passed to the next layer. The next layer is computing perhaps more abstract features. So the early layers might extract local, low-level features, such as, for example, edge detectors, while the later layers might extract more abstract, more global features, such as maybe object parts. Well, last year, in a paper with Xiaoji and Zico, we questioned this basic story in the domain of natural language processing and sequence modeling. And many of our ideas there in these deep equilibrium models that we introduced last year in the context of language modeling. Many of the ideas there have inspired our new work on multi-scale deep equilibrium models that are now applied to computer vision. So, before I proceed to multi-scale deep equilibrium models and computer vision, I will briefly review what we did last year with the basic deep equilibrium models, DEX, as we call them, in language modeling. The first step was to take a conventional deep network with layers. Each layer has its own parameters, and say, why don't we make all the layers the same? What if each layer is the same? They're all the same. We tie their parameters, and we simply repeat the application of an identical layer. We take a layer and simply apply it many times with the same parameters. This might seem like a big restriction in expressive power, but turns out it is not. Formally, we have shown that any deep network can be converted to a weight-tied deep network where all layers are the same, strictly the same, exactly the same structure, exactly the same parameters. And this conversion retains the depth of the network and retains the expressive power. Essentially, any deep network can be expressed as a weight-tied deep network without giving up any expressive power. Furthermore, we and other teams have shown that weight-tied deep networks, where again, each layer is the same, you just apply the same layer many times, weight-tied deep networks are empirically as strong as non-weight-tied deep networks, at least in the domain of natural language processing. So, that was the first step. Why don't we make all layers the same? Here is the next step. What if we don't need explicit layers at all? If we're the same, can we just say that we have one layer? We're going to do this in the following sense. Think what happens if you now have the same layer and you're applying it many times, you're stacking it. Well, imagine, as a thought experiment, applying it an infinite number of times. What is going to happen? Is this even well defined? Here's one way to think of it. Think of a ResNet 1000 residual layers. And now apply the residual layer one more time. So from a ResNet 1000, you go to a ResNet 1001. Do you expect much to change? Do you expect a big difference? No. No. Generally, the ResNet 1001 is going to be essentially the same as the ResNet 1000. This is the basic intuition behind deep equilibrium models. Deep equilibrium models say that we can simulate an infinite number of applications of the same layer just by positing an analytical equilibrium condition. The condition is that another application of the layer makes no difference. Another application of the layer makes no difference. If Z is the input to the layer, then the condition is f of Z minus Z equals 0. So at equilibrium, the layer makes no difference. The layer is the function f. We apply the layer to its input, we look at the output, and nothing changed. That is the condition that holds at equilibrium. So, deep equilibrium models model this condition analytically. They say, we only have one layer, and we are going to solve for what happens in the limit at equilibrium when applying this layer makes no more difference. First of all, this can be done without actually applying the layers, without unrolling the layers. We can solve for the equilibrium point analytically. We can look at the equation f of z minus z equals 0 and apply root finding solvers such as quasi-Newton methods to solve for the feature vector at which this holds, for which this equilibrium condition holds. And at training, we can train for the parameters of the model, the parameters of this layer, without actually tracing through the forward solver. We can define the gradient analytically via implicit differentiation and compute the gradient analytically without actually unrolling the forward solver and without tracing through the individual steps of the forward solver by conventional auto differentiation. So this is a radically different model. This is a radically different approach to deep learning, in which, for example, there is no computational graph in the standard conception of the term. Backpropagation and gradient-based optimization proceeds not by stepping backwards through the computational graph of the inference procedure. In fact, the inference procedure and the gradient computation are very different. They can be performed by different solvers, and they don't proceed through the same computational graph at all. Now, here is a multi-scale deep equilibrium model. What you see on this slide is the whole model. There's nothing hidden. This is it. This in the middle is the layer. The middle part of this figure is the Mdeck, the multi-scale deep equilibrium model layer. What you see is that there is a feature tensor that is taken through a residual block. This happens at multiple resolution, and in practice we use 4 resolutions, exactly as you see on this slide. The input is provided at full resolution, but the model internally maintains 3 other lower resolutions. Each is lower than the preceding one by 2 by 2. Features at these different resolutions are intermixed. The yellow and blue arrows you see here convey information from one resolution level to another via either bilinear upsampling or parameterized convolutional downsampling. What you get after this mixing is a feature tensor at each resolution. These feature tensors and the different resolutions exist side by side, simultaneously, and the equilibrium condition is that the feature tensor at each resolution, after this processing, after the residual block and mixing in information from the other resolutions, is the same that it was at input to the Mdeck layer. So the feature tensor at each resolution at output is the same that it was before applying these processing steps inside the layer. That is the equilibrium condition, and that is it. One layer that is analytically solved for this equilibrium condition, which basically says that the application of this layer makes no difference. For completeness, I will show you what happens inside these green residual blocks that you saw before. So you saw these little residual blocks here at each resolution level. They're basically standard residual blocks, two applications of convolution with some nonlinearities and normalization. And in a couple of slides, you will see that we have a number of different Mdecks at different sizes. There is a small Mdeck, there's a large Mdeck. You might ask, if that was the whole model, what's the difference between the small Mdeck and a large Mdeck and an extra large Mdeck? The differences are just in the width of these feature tensors and the number of channels in the convolution operator. That's it. Structurally, the models are identical. The only difference is the width of the activations that the model maintains and the number of channels in the convolution. Now, I hope you are realizing by now that the Mdeck is a radically different model from convolutional networks. So on the left, you see a typical convolutional network. And for example, if we train a convolutional network on ImageNet classification and then transfer it to a dense prediction task like semantic segmentation on the cityscapes data set, we would take the encoder from ImageNet classification, which is a residual backbone, and we would keep the backbone and attach maybe a decoder to it, and then train this whole thing, which now has a different structure because of the decoder. We train the whole thing on semantic segmentation. On the right, you see the Mdeck that is applied to both image recognition, for example, on ImageNet, and semantic segmentation, for example, on cityscapes. And the Mdeck is its own backbone. Exactly the same model is applied to image classification and semantic segmentation. The Mdeck is its own backbone because it conveniently exposes interfaces at different levels of resolution. At equilibrium, it has these feature tensors that are all synchronized, that all have different resolutions, from the full resolution feature tensor that can be used for semantic segmentation to a low resolution feature tensor that can be used for recognition. So we apply exactly the same model to ImageNet classification and high resolution dense prediction, for example, on the cityscapes data set. Let's look at some results. Here are the results on ImageNet classification. Let's start with the top part of this table, where we are looking at fairly small models appropriate, for example, for deployment on mobile platforms such as smartphones. So here, a small Mdeck has the size that's roughly between ResNet 18 and ResNet 34. So in terms of the number of parameters, this small Mdeck is roughly between ResNet 18 and ResNet 34. But in terms of accuracy, it outperforms ResNet 50. Now, that alone is absolutely remarkable because ResNet 50 is a strong model. It is an amazing model. And we are now showing that we can get ResNet 50 level accuracy on ImageNet with a single layer, with a radically different model that really only uses a single layer with an analytical equilibrium condition. A radically different approach to deep learning in this domain. Let's look now at the bottom part of this table, where we see the performance of a big Mdeck. So here, setting aside capacity considerations, this big Mdeck, still a single layer model, just a thicker one. You know, the width of this layer, the number of channels in the layer is just bigger. This Mdeck XL passes the 79% top 1 accuracy threshold on ImageNet. A remarkable performance for an implicit model that basically has only one layer. Now let's look at semantic segmentation on cityscapes. Now, cityscapes is a challenging data set of high resolution road scenes where each image is of size 2 megapixels, so roughly 2 million pixels per image. And let's look at some convolutional networks and Mdecks. And again, the Mdecks here are the same. They're identical in structure, identical to the Mdecks that we just used for ImageNet classification. Now, in the top half of this table, you will again see small models appropriate for edge deployment, mobile deployment. And we will compare the performance of our small Mdeck to a MobileNet V2+, which is a strong, carefully crafted convolutional network that was published just 2 years ago at CVPR 2018 and was carefully architected by a very competent, very experienced computer vision team. And what we see is that the small Mdeck, with a comparable number of parameters, actually a bit smaller than MobileNet V2+, surpasses its accuracy. So the Mdeck outperforms a strong convolutional network that was published only 2 years ago, while taking a radically different approach that has only a single layer, a radically different approach to modeling in this field. Let's now look at the bottom part of this table, where we see the performance of a large Mdeck. This is the Mdeck XL. This now has a higher number of parameters. So setting aside capacity considerations, we're just going to look at absolute accuracy. After all, if you perform well on the Cityscapes leaderboard, the question of how many parameters you used is a bit secondary. It is a comparison in absolute numbers. And here we see that in absolute numbers, the Mdeck XL surpasses the 80% threshold in mean intersection over union, which is amazing because it's much stronger than very strong models that were developed only 2-3 years ago. Very well-known convolutional networks such as PSPNet, DeepLab V3, and PSANet, which are strong convolutional networks, carefully crafted, carefully architected by very experienced, very competent teams of computer vision researchers. And you see that the Mdeck, which takes a radically different approach, outperforms these very strong recent models. Here are some segmentation results to give you a sense of what the Mdeck produces on the Cityscapes dataset. And I can tell you that these are excellent. I've been working on semantic segmentation for about a decade now, and these are just excellent semantic segmentation results. You see clearly delineated objects with sharp boundaries that closely adhere to object boundaries. It is amazing to me that such results are produced by a model that is essentially unlike anything else in this field. Essentially a shallow, single layer model that operates based on radically different principles than other models in this field. The takeaway for this second part of the talk, which we are now concluding, is that there is a radically different approach to differentiable modeling. This implicit deep learning approach, which the Mdeck exemplifies, proceeds along very different assumptions from standard deep networks, including convolutional networks. And in particular, it basically dispenses with the layer-wise architectures that we've come to associate with deep learning itself. And it raises the question, do we actually need carefully structured, carefully architected, layer by layer models? Maybe there is a radically different approach that doesn't involve these layer-wise structures that is perhaps just as effective, perhaps in some ways more effective. And this last point is particularly intriguing, given that this whole approach of implicit deep learning has essentially gone from toy domains such as MNIST to, as you see today, megapixel level image parsing in 2 years. So 2 years ago, the most advanced applications of implicit deep learning, of the kinds of models that we looked at in the last 20 minutes, the state of the art was doing handwritten digit recognition on the MNIST dataset. Yet today, we are getting competitive results on ImageNet, image recognition, and on Cityscape's semantic segmentation, basically the cutting edge of computer vision with megapixel scale images. That whole advance happened in 2 years. And I'm really looking forward to seeing what happens next. The final point I want to make is that both projects were driven by curiosity. These are both examples of curiosity-driven research, where we essentially looked at the basic assumptions being made in computer vision today, and we questioned these assumptions simply out of curiosity. Do we need convolutions? Do we need layers? I don't really have anything against convolutions or against layers, but I love questioning assumptions. And I encourage all of you to engage in this kind of curiosity-driven research where you re-examine the very basic assumptions of the field, assumptions that are so pervasive that they're often not even articulated, like the assumption that deep networks are deep. I encourage you to engage in this kind of curiosity-driven research, because often it does make remarkable impact on practice, and it does yield results that are empirically very, very strong, but also because it's just so much fun. Thank you very much.